Muy buenos días a todos. Bienvenidos a este segundo día del ciclo de conferencias ADITIVA Querétaro 2020. El día de hoy tendremos la participación de 3 invitados especiales con 3 ponencias. Comenzamos ahorita con la ponencia del Dr. Frederick. Contamos con una segunda ponencia a las 11:30 y cerramos el ciclo a las 3 de la tarde con la última conferencia. Recuerdo que tenemos una caja en la plataforma para preguntas y respuestas que pueden estar anotando durante la sesión, y al final de la sesión tendremos un espacio donde nuestros invitados nos estarán dando respuestas a esas preguntas. Entonces los invitamos a poner sus preguntas en ese espacio. Y bueno, ahora voy a hacer la presentación del doctor. El doctor Frederick está conectado desde Francia, entonces me voy a permitir cambiar al idioma inglés para presentarlo. Frederick, welcome. Frederick de Chambon holds a doctorate in material science from the School of Mines in Paris, in France. He has been working for 20 years as an assistant professor and then full professor at the University of Montpellier, France, where he has developed research activities on arc welding process and since 2015 on additive manufacturing process based on the electric arc known as WAM. He also participated in the creation of several bachelor's and engineering level training courses specialized in welding. He was head of the Mechanical Engineering Department at the Technology Institute of Nimes from 2010 to 2016, and from 2011 to 2019, head of the Welded Assembly Research Team at the Mechanic and Civil Engineering Laboratory at the University of Montpellier. Thank you so much, Dr. Frederick, for being part of these seminars. Please take the word.
Thank you for your introduction. Buenos dias, good morning. Thank you also for your invitation and to participate to this seminar on additive manufacturing. So my talk has been recorded. So now I will show my presentation, and I stay here, of course, for the end to answer to all your questions at the end of my presentation. So now I'll show you my presentation. Oh, sorry. Okay. Good morning, everyone. My talk concerns some current researches achieved at the University of Montpellier in France on the wire arc additive manufacturing process. That concerns the work of many contributors listed here that I would like to thank. The additive manufacturing is now extensively studied by numerous research teams. This slide illustrates the main steps leading to the development of a product by additive manufacturing and some research fields associated with these different steps. Some researches are focused on the optimization of the CAD model using the advantages of the AIM process by topological optimization, for instance. Some other works are focused on the optimization of the build-up strategy defined by the slicing strategy of the component shape. Other research works concern the optimization of the process parameters and the online control of the process. Finally, many works are focused on the characterization of the materials obtained by additive manufacturing processes, including the effects of finishing treatments like heat treatment. In our research team, we are mainly focused on these two last fields applied to the wire arc additive manufacturing process. I will present some of the issues identified in these fields and some results obtained. My talk is divided in 7 parts. First, I will present the main characteristics of the wire arc additive manufacturing process. Then I will present the cold metal transfer arc welding process used in our team as heating source for the wire arc additive manufacturing process. In a third part, I will present some advances concerning the optimization of the arc process parameters. Then I will speak about the online monitoring of the process in order to try to detect a deviation of the process. In the fifth part, I will present some results of materials characterization, and the sixth part will be focused on some modeling results. Finally, I will show some perspectives of our works. So the first part is dedicated to a general presentation of the wire arc additive manufacturing process. Here is a presentation of the main additive manufacturing processes dedicated to the metallic materials, classified considering the state of the used raw material and the heating source. The powder bed technologies, based on the deposit of successive powder layers locally melted or sintered by a laser or an electron beam, are probably the most used. Other techniques are based on the spray of powders that are melted by a heat source, generally a laser or plasma.
The wire-based technologies have been less developed so far. With these technologies, a metal wire is melted using a laser, or, in the case of the WAM process, using an electric arc. In a general way, the WAM process does not allow the same precision shapes of the manufacturing components as the powder bed technologies. However, it presents some advantages compared to the other additive manufacturing processes. First, there is no technical limit to the size of the manufactured samples because there is no manufacturing chamber with it. For comparison, the powder bed technologies are limited to the manufacture of components not exceeding about 400 mm size, and the spray technologies are limited to component size of about 1 meter long. Another advantage of the WAM process is its deposit rate, higher than other additive manufacturing processes, as given in this graph. This is of particular interest for the manufacturing of large components to reduce the manufacturing time. In addition, as this process uses the same raw material as the welding process, a great number of materials grades are available. The wire raw materials are also less expensive than the powder raw materials. Finally, the wire arc additive manufacturing process offers some advantages due to the massive shape of the filler metal that does not present the safety problems and the storage problems of the powder-shaped materials that can be easily inhaled or polluted. The WAM process described in this picture consists in melting a metallic wire with an electric arc and to deposit the liquid droplets to form layers. Ignition and control of the electric arc as well as the wire feeding are achieved using an arc welding device. One can see on this video the deposit of layers of an aluminum alloy with the WAM process. The WAM technology is composed of three main elements. The wire feed device that allows compensating the melting and deposit of the wire end, the arc control process, and finally, the 3D positioning or moving device of the deposit head. As was said previously, the wire feed device and the arc control process in the WAM process are similar than that used on arc welding processes. One can see on this picture two kinds of WAM devices corresponding to two kinds of 3D moving solutions. The first one is derived from a 3D printer and constitutes a low-cost WAM device. One can see on the video manufacturing with this device of an aluminum tubular piece on a plate. The second device is an industrial WAM production device composed of two welding robots with a welding station. Here is a manufacturing sequence showing the production of a complex shape shell with this device. In this picture, one can see some examples of components for which the WAM process is of interest. These kind of shell shapes are difficult to obtain with conventional processes or rather costly. So the WAM process is a convenient process for manufacturing shell structure with complex shapes, having a thickness up to about 10 millimeters, which is the maximal thickness of the layers that can be deposited with this process. I will now present the CMT arc process, which is a welding process retained for our WAM devices. The CMT process is a derivative process of the classical metal inert gas or MIG welding process, also called gas metal arc welding process. With this process, a filler wire is automatically fed and its end is melted using an electrical arc created between the wire tip and the welded samples by a welding generator. According to the wire diameter and the arc power, various melting modes corresponding to different metal transfer regimes can be observed. When the arc power is low, the wire tip melts slowly and the wire, which is continuously fed, enters regularly in contact with the melt pool formed at the surface of the welded samples, creating a short circuit on the arc extinction. This transfer regime is called short circuit mode and is a stable mode because the formed deposits are rather regular. When the arc power increases, the melting of the wire tip is faster and some large liquid droplets are sprayed, producing sputters and sometimes irregular deposits. This transfer regime is called the globular mode. Finally, when the arc power is higher, the liquid droplets are smaller and more regular and are sprayed axially, producing a regular deposit. This transfer regime is called the axial spray mode. The axial spray mode produces also a strong heating of the produced samples that can require the cooling of the component and a delay before to proceed the manufacturing. For this reason, the short circuit mode is preferred for additive manufacturing with the WAM process based on the MIG arc welding process. The CMT process has been developed by the Fronius company to improve the regularity and the stability of the deposit obtained with the MIG process in short circuit mode. This process is considered as a MIG process using a controlled short circuit mode. With this process, droplets of liquid metal are deposited according to a regular cycle comprising 4 main steps. The filler wire is fed or retracted according to the step in the deposit cycle. In the first step of the cycle, the arc melts the wire tip and the wire is fed towards the workpiece. Then, the liquid drop formed at the wire tip enter in contact with the workpiece surface, producing a short circuit on the arc extension. In the third step, the wire is retracted up to its separation of the workpiece, leaving the drop of liquid metal deposited to solidify on the workpiece. Finally, the electric arc is reignited and a new cycle begins. During the transfer cycle, the electric current changes. During the beginning of the arc phase, a current pulse is created with a control current and a control duration. This phase is called the Bose phase in red in the figure. Then, the arc current decreases to avoid an excessive growth of the droplet and its detachment, and the wire is fed toward the workpiece. This phase is called the wait phase in blue. Finally, when the wire tip enters in contact with the deposit and produces a short circuit, the current changes again up to a given value, chosen to maintain the heating of the liquid drop up to its detachment. The wire is then retracted up its detachment on a new arc phase. This phase is called the short circuit phase in green color here. One can see again on this slide the 3 phases of the CMT cycles and the main process parameters controlling this phase. The boost phase is mainly controlled by the boost current, high boost, and the pulse duration, T boost. The wait phase is mainly controlled by the wait current, high weight, and the feeding weight of the wire, VF. Finally, the short circuit phase is controlled mainly by the short circuit current, ISC, and also by the retract speed of the wire, depending on the feeding weight, VF. I will now present some results concerning the optimization of the ALC process parameters in order to improve the deposit's characteristics. The optimization of the process parameters requires a good knowledge of the effect of the various process parameters on the coupling on the melting phenomenon, on the liquid metal transfer, and on the spreading on the already formed deposit. In order to study the stability and the regularity of these phenomena according to the process parameters, two kinds of data are recorded during the process. Video recordings are obtained using a high-speed camera. An ambroscopic technique has been used to observe the deposited metal shape through the electric arc. For that, an halogen light is placed behind the wire tip that allows observing the contour of the deposit despite the arc radiation. In addition, the electric parameters, voltage and current, are recorded with a high acquisition frequency to follow the stability of the different phases of the CMT cycle. The ALC process parameters can act on three main kinds of characteristics on the deposit. First, they act on the geometry of the deposit, that can be evaluated, for instance, by its thickness, its height, but also by the wetting angle. Secondly, they act on the deposit rate, that can be increased to decrease the manufacturing time. And finally, they act on the stability of the deposit cycle, which can act on the regularity of the deposit shape. The first example of process parameters optimization that I will present concerns a study focused on the increase of the deposit rate. The first option to increase the deposit rate consists to increase the wire diameter. For some current materials, the welding devices allow to use wire up to 1.6 mm in diameter. However, these wire sizes are not available for all the materials, the standard diameter of the wire being 1 or 1.2 mm. The second option consists, of course, in optimizing the process parameters. The deposit rate depends on many factors, as the wire feed rate, the current of the various phases of the transfer cycle, or the duration of this phase. However, two factors were identified to have the greatest influence: the intensity and the duration of the boost phase. The value of the boost phase current can be changed between about 20 and 300 amperes, and the duration of the boost phase can be changed between 0 and about 10 milliseconds. Here are two video recordings showing the effect of the pulse duration. The first video shows the wire tip evolution for a short pulse time of 1 millisecond. One can see on the formation of a small drop at the wire tip that stays on the wire tip up to the short circuit. The second video shows the wire tip for a long pulse duration of 10 milliseconds. One can see the droplets formed at the wire tip are too big to remain attached on the wire tip and are sprayed on the surface, producing sputters. So the increase of the pulse duration increases the melting rate of the wire, but it promotes also the formation of sputters. The limit values has to be identified, depending also on other parameters, as the current value of the boost phase. One can see on this slide the effect of the variation of the boost phase current and duration on the deposit geometry for a steel. An increase of the boost current increases the volume and the temperature of the deposited metal, that creates a better wetting. However, an excessive burst current also creates a vaporing of the wire metal, resulting in a porous deposit. An increase of the pulse duration also increases the width of the deposit and improves the wetting. But, as described before, an excessive increase also produces sputters, observed in the white cycle in the micrograph. The optimization of the process parameters has been conducted in order to increase the deposit rate without creation of porosity and sputters. This graphic shows the deposit rates obtained with the synergic points of the CNT process for a steel wire. The synergic points correspond to parameters set pre-recorded in the welding process for a given material to obtain a stable and regular metal transfer. One can see that the maximum deposit rate allowed with this parameter set is about 3.5 kg by hour. Thanks to the optimization of the process parameters, a new synergic point has been added, allowing a deposit rate of more than 4 kg by hour. That corresponds to an increase of about 20% compared to the maximum deposit rate allowed with the pre-recorded parameters. I will now present another issue to comprehend that have required an optimization of the process parameters. It concerns the reduction of geometrical flaws frequently observed at the beginning of the deposit, mainly in aluminum alloys. One can see on this picture, corresponding to a scanning of a real deposit, an irregular shape of the beginning of the deposited bed. This kind of defect is frequently observed and can be attributed to a pressure variation in the liquid according to the curvature of the liquid-gas interface. Indeed, the pressure variation in the liquid deposit can be expressed with a Laplace equation that indicates the pressure in the liquid increases when the curvature radius of the liquid-gas interface decreases. In this figure, one can see that if the contact angle of the liquid deposit on a solid substrate is higher than 90 degrees, an increase of the bed height creates a decrease of the radius, and then a pressure increase. That promotes the formation of a constant height all along the bed, and so a regular deposit. At the opposite, when the contact angle is below 90 degrees, then an increase of the bed height produces an increase of the curvature radius, and so a decrease of the pressure into the liquid. This pressure decrease promotes the suction of the neighboring liquid having a lower curvature radius, conducting to the formation of a narrow neck just after the beginning of the deposited bed. One can see on the video here the formation of this kind of flow. The wetting of the liquid on a solid substrate is very bad at the beginning of a deposit, producing an increase of the curvature radius with the increase of the deposit height, and so a pressure decrease that promotes the further increase of the deposit of the deposit height. We can see the newly deposited droplets are sucked towards the rear of the bed, forming a narrow area in the front of the deposit until the rear of the deposit solidifies and stops the phenomenon. This kind of defect can be reduced by improving the wetting of the liquid at the beginning of the deposit. This is possible by promoting the heating of the substrate at the beginning of the deposit using an optimized ignition cycle.
By imposing a high arc intensity during the emission cycle, small droplets are formed at the wire tip and sprayed on the surface of the substrate. These small droplets produced by a high-power electrical arc have a very high temperature and then favors the heating of the substrate surface before the beginning of the CMT cycles, corresponding to the deposit of larger or less hot droplets. One can see on the video the melting and spray of these small droplets that create a very hot melt pool with a better wetting of the substrate before the first short circuit at the beginning of the CMT cycle. So the optimization of the emission cycle allows to reduce drastically the geometrical defect observed at the beginning of the aluminum alloy, as shown on this photo.
The following part concerns some of our research work on the monitoring of the process in order to detect or prevent the defect formation. The main goal of these researches is to monitor the deposit characteristics in order to be able to adjust the process parameters in case of process deviation. For that purpose, two kinds of data recording previously described can be used to develop methods based on image analysis or on the treatment of electrical signals of the arc. When a process deviation is observed, two strategies can be followed to adjust the process. The first one consists to modify the building strategy, that is to say, to adjust the trajectories of the welding torch. The second one consists in changing the arc process parameters corresponding to the main CMT parameters previously discussed, or the travel speed of the welding head. I present here a method developed by image analysis to follow online the geometry of filar structures obtained by the superposition of semi-spherical beds. For the video monitoring of the process, two cameras are used, positioned as indicated in this picture. The first camera allows to monitor the location of the center of each new deposited bed, and the second one is used for a contour detection of the surface for each new bed.
Based on this monitoring system, a retroaction loop has been developed to adjust the bed strategy in real time. For that, the real bed contour obtained is first compared to a predicted contour, and a real-time retroaction loop has been computed for repositioning the welding gun at each new deposit. In this video, we can see the real construction and the predicted one for a complex filariform structure. Note that the build speed is greatly accelerated on this video, the real manufacturing time of this component being about 8 hours. The image recording, unfortunately, is not always a convenient technique, especially for the building of massive structure, where the contour detection is not possible. In addition, the data recorded are often too big for real-time and online control of the process.
A second strategy has been investigated for the online control of the process based on the monitoring of the electrical parameters of the process. The current and voltage can be easily recorded, and the online treatment of this data is more simple and faster than for image treatments. In order to try to detect geometrical flows from the electrical recording, The three phases of the CMT cycle, the boost, the wait, and the short circuit phases, are automatically detected, and some parameters of this phase are computed as the power, energy, duration, mean intensity, mean voltage for each phase of each cycle. These results were compared to the geometry of numerous deposits obtained with various process parameters. This work has shown that some of the computed parameters are good indicators of the geometrical defect. In particular, the mean voltage of the wait phase and the duration of the wait phase seems to be correlated to the height variation of the deposits. These parameters can be then monitored in order to detect geometrical flaws on the deposit and to correct the process parameters when critical flaws are detected. For that purpose, a statistical process control method has been introduced. First, the control limits are defined as the process capability for a stable process without geometrical flaws. Then, control charts are computed to follow the stability of the process. A process is under control when the points of the control chart are inside the control limits. At the opposite, a process is control when the points of the control chart are outside the control limits. One can see on this slide the evolution of the written parameters, the voltage and the duration of the wait phase of the CMT process for a regular deposit without geometrical flaws. The average values of the standard and the standard deviation of each parameter are computed, and the upper and lower control limits are defined. This slide shows an application of the SPC method to the monitoring of the deposit of steel beads. Here is a control chart computed for the duration of the wait phase. This control chart indicates a process out of control, several points of the control chart being below or above the control limits. This result is confirmed by the observation of the deposit irregular. This kind of height variation of the beads is generally due to a too lower arc current. For the next deposited layers, the current of the boost phase has been increased to 160 amperes, allowing to improve the regularity of the bead. The control chart of the wait phase duration indicates a process under control, except at the beginning of the bead, due to an accumulation of metal produced by the initial cycle. The next section concerns the characterization of the produced materials. The microstructure of the materials obtained with the WAM process and the corresponding mechanical properties are rather particular. Indeed, the solidification processes imply specific microstructure and behavior, in particular, an out-of-equilibrium microstructure due to the rapid cooling, an anisotropic microstructure due to a directional solidification phenomenon, a corresponding anisotropic mechanical behavior, an inhomogeneous structures and mechanical behavior, and a low fatigue strength, mainly due to the microstructural defects and to the residual stresses formed during the process. All these factors depend strongly on the process parameters and post-treatment. Here is an example of microstructure obtained for a 316L stainless steel produced with the WAM process. Due to the rapid solidification and cooling, a skeletal delta ferrite is formed in the austenite dendrites that can have a detrimental effect on the mechanical properties. The content of the delta ferrite depends on the process parameters, an increase of the energy produced by the increase of the arc power, producing a significant decrease of the ferrite content. The manufacturing components in a 316L stainless steel can be sometimes used in a as-built state, but generally, heat treatments are applied on the components. These heat treatments can be stress release treatments at a temperature of about 550 degrees Celsius, or complete annealing treatments at temperature of about 1100 degrees Celsius. These heat treatments change the material microstructure, and especially the content of the delta ferrite, as one can see on the micrograph. In order to observe the effect of the heat treatment of this detrimental phase, we have quantified the content of the delta ferrite in cross-sections using an image analysis techniques. We observe the stress release heat treatment allows to decrease the content of the delta ferrite from about 9% to 6%. However, an annealing heat treatment allows to dissolve a larger part of the delta ferrite formed at the solidification. Another specificity of the materials obtained with the WAM process is a strongly oriented grain structure. This is because the solidification is highly directional, because the thermal gradient is oriented mainly in the build direction. Consequently, the grains have a columnar morphology, as we can see on the picture on the left side of this slide. In addition, the growth direction is a FCC structure, being the 100 crystallographic direction. The material has a crystallographic texture, as shown the pole figure obtained from EBSD analysis of the material. One can see on this figure the 100 crystallographic axis of the grain is mainly oriented in the Z direction, corresponding to the build direction. This material's texture has a consequence on its mechanical behavior. One can see on this slide the tensile curves obtained on samples of titanium alloys Ti6V produced with the WAM process. The tensile behavior of the materials is different when the tensile specimen axis is the vertical direction, corresponding to the build direction, or to the horizontal direction, corresponding to the direction transverse to the building direction. In the case of these materials, the yield stress is higher in the horizontal direction and the elongation is lower. This behavior can be correlated to the columnar grain structure, producing a higher strength in the direction of the grain thickness compared to the direction of the grain's length. In order to better understand the mechanical behavior of such samples, a digital image correlation method can be used. This technique allows to compare the mechanical behavior of the various areas of an heterogeneous sample by following the strain distribution of the sample surface. This slide illustrates the results of strain measurements by DIC method on samples of 316L stainless steel obtained by WAM process. One can see on the strain map that the strain varies on the samples due to the microstructural heterogeneities. On the horizontal tensile specimens, an atypical behavior is observed that was not still explained, with several frictions in the sample. On the vertical specimen, the strain is mainly localized in the center of the successive layers, the interface between two layers being less strained, possibly due to finer microstructure in the interface between two layers. Another mechanical property that can be unconventional in WAM materials is the fatigue behavior. Some first fatigue tests were achieved also on 316 Hale stainless steel samples, and only the fatigue limit has been studied for the moment. To estimate this limit, a method based on the measurement of the heat dissipation of samples submitted to a given stress amplitude is used. Series of 3000 cycles at a given stress amplitude are applied on the samples, with increasing the stress amplitude at each new series, as described on the left figure of this slide. The heat dissipated by the sample is measured using an infrared camera. The stabilized temperature versus the stress amplitude is given in the right figure. The stabilized temperature increases linearly, and then an increase is observed above a stress level that corresponds to the fatigue limit, as confirmed by some recent studies. The fatigue limits obtained with two WAM process parameters on samples of 316L were compared. The fatigue limits in the build direction and in the horizontal direction were also compared. The obtained value for the fatigue limits are whether high compared to the yield stress of the material or compared to some literature data on 316L materials obtained by conventional routes. Despite a rather large dispersion of the results, one can see that the fatigue limit seems slightly higher on samples manufacturing with a lower power. In addition, the fatigue limit seems better in the build direction than the horizontal direction. Before to finish this talk, I will present some current studies concerning the numerical modeling of the WAM process. The main goals of this numerical modeling are to predict the material characteristics and to reach a better understanding of the physical phenomena involved during the process. Two kinds of results are expected in our current modeling work: the prediction of the formed microstructure in order to predict the anisotropic behavior of the material, and the prediction of the residual stresses and distortions in order to try to optimize the build strategy to reduce the stresses or the distortions. Here are some first results concerning the modeling of the solidification grain structure obtained on a 316L stainless steel in additive manufacturing. These results concern the selective laser melting process, but the same kind of study is also in progress on the WAM process with our French partners. For this modeling, the CAFI method is used, that couple a finite element method to predict the evolution of thermal fields during the AM process, and a cellular automata method to model the grain growth during the solidification process. One can see on this slide a comparison of cross-sections of the simulated grain structures obtained with two different process parameters corresponding to various energy levels. The grain structures are rather similar, but a slightly higher grain size is obtained when the heat energy is higher. Finally, we are also working on the numerical simulation of the residual stresses and distortions produced in WAM. The main goal of this project is to develop a numerical tool allowing to optimize the build conditions in order to reduce residual stresses and distortion. To validate the modeling, an experimental device has been developed, consisting in depositing layers to form a wall on the edge of a steel plate. The experimental device is instrumented to measure during the WAM deposit the temperature evolution with thermocouples and the displacement of the plate using a laser displacement measuring system. In addition, residual stress measurements have been done by neutron diffraction. The validation of the modeling has been done by confronting the temperature cycles and the displacement evolutions predicted by the model and with experimental measurements. And finally, the predicted residual stresses have been compared with the results of neutron diffraction measurements. Here is a comparison of the predicted and measured longitudinal residual stresses along a vertical cutting axis, crossing the substrate plate and the deposited layers, and show a good correlation between experiment and numerical prediction. I will finish my talk with some perspectives of our current works. In the field of the process control and improvement, we have still to improve the knowledge of the effect of each parameters of the CMT process on the mechanism of melting of the wire tip and on the deposit of the molten droplets. Concerning the online monitoring of the process, one can consider to introduce the control chart method based on the monitoring and treatment of the electrical parameter in a real-time process to develop a retroaction loop and to correct the process deviation. Concerning the materials characterization, it seems important to have a better understanding of the effect of the microstructure on its anisotropy, on the mechanical behavior, and on the fatigue damaging. Finally, on the field of the modeling, we are working to develop the CAFI method for the WAM process in a collaborative work with several fetch partners to predict the formed grain structure. In addition, we need to identify behavior laws of various materials and to improve the modeling strategy to predict the residual stresses and distortion in various materials. Thank you for your attention.
Well, thank you, Frederick, for your presentation. Thank you all the attendants too. Good morning here, good afternoon there in France, or who can be hearing or listening to us there. This is a really interesting and illustrative presentation. I think for some groups here in Mexico, it's really interesting to the implementation of WAM. So we have some questions about. We will start with one from Jose Alejandro. He's asking me about the configuration, the cinematic configuration. I think it's about the mechanism of the robots you are using. What kind of robots or mechanisms do you use to implement WAM? Because I think he didn't understand the kind of mechanism you use to implement the process.
With the 3D printer, This is your work, Arturo. It's a Cartesian cinematic. It seems the more convenient for this kind of application, because for one process, the welding torch have a weight. The weight of the welding torch is rather high. So the Cartesian mechanism seems the more convenient for this kind of application. This was the work of Arturo during his PhD. So he investigates other mechanisms and decides to choose these Cartesian mechanisms. Maybe you can explain your shocks, Arturo, if you want.
Well, thank you, Fred. Yeah, for everyone who doesn't know, yeah, I was working with Frederick in France for my PhD, and yeah, exactly, we use a Cartesian mechanism, a cinematic mechanism to Cartesian to make work the process one. No? It was a cheap configuration and not expensive. And it works well because we didn't need to move the torch. We could have it fixed. And well, but you can see in many examples in many other configurations that the robots or robotic arms are really good to use in these applications. It depends the deepness you want to have in the topic, I think, with one, no? The things you want to do. But well, thank you, Fred. I will continue with the other questions from Enrique. I think he's a researcher here with us. He's asking us about the microstructure differences, but using low and high energy. If you think that this is a function of the solidification rate, or how do you explain the difference in microstructure with different energy?
Concerning the stainless steel, the differences observed on the delta ferrite content is probably due to the solidification rate variation. Yes, it's probably that. For other materials, there is also effect of the thermal gradient after the solidification, during the solidification also. But we didn't observe real modification. One of our goals was to try to obtain equiaxed grains, because as I showed in my presentation, the structure obtained with this process is generally highly columnar, and it gives anisotropic behaviors that can be an issue for certain applications. And our goal was to try to obtain columnar grain structure by modifying the deposit rate, the heat input, the travel speed. But we didn't get this kind of microstructure. I think it's possible to obtain a columnar to equiaxed transition with some materials, but we have to work on the composition of the material. And concerning the stainless steel, yes, the difference in the delta ferrite was due to change in solidification rate.
Perfect. Thank you. Have many other questions. For example, from Emmanuel Reyes, that is a PhD student here. He's asking us if you know if there is an acceptable deposit height or width ratio or an aspect ratio for CMT1 deposit bit. You consider that there is an aspect ratio acceptable?
the ratio between height and width.
Yeah.
It depends. The surface state is rather bad with this process. So a finishing by machining is often required. So the surface state is not really a criteria. For an order of size, the ratio between height and width may be 0.5, maybe 0.3, 0.5. For a width of about 5 to 6 millimeters, we can obtain a height of about 2-3 millimeters with a rather good shape.
Okay, thank you. He has another questions, but I will continue with some from Jose Mercado. He thanks for the presentation and tell us what is the process you use to move from the CAD model to the machine code. He comments that he shows we use a 2.5 degree system, and what are the challenges in adding supports structures to complex shapes. There are some two questions, I think. One is, how do you move from a CAD model to the machine, and what are the considerations in supports if you are using supports?
Considering the moving system, I'm not a specialist. This is the work of one of my colleagues. He developed an algorithm to optimize the building strategy, including the moving of the torch with 4 or 5 axes. But I'm not a specialist. I can't answer to this question. Sorry. On the second one.
Yeah, what are the challenges in adding support structures in complex shapes?
I don't really understand.
I think he's asking if you use support structures when you are printing something there.
Oh, we have the supports are not necessary with this process. The layers are added without supports. We have just a plate, a substrate plate. It's a plate with a high thickness of about 5 to 10 millimeters, and then there is no supports. The layers are deposited without any other supports.
Okay, thank you.
The piece can rotate to facilitate the deposit for each new layer, but there is no support.
Yeah. Okay. All right. Thank you, Fred. We have another question from Luis Corona. You know him. He first congratulates you for your presentation and your work team. He asked you. He said that now that you understand and master one process, do you plan to combine one with traditional manufacturing to create a kind of hybrid process to produce end-use parts? I think he's asking what is the next after one. Do you think that we have to combine it?
No, we don't have plan concerning the combining of other process like machining. Some devices exist combining deposit with WAM and machining, but we are in our team. We are a small team, and we are specialists of the ARC process only. We don't have a special knowledge on machining process. So no plan on this side.
Thank you. I have another question from Itzel. She's asking us about the mechanical capabilities that you show, if they were tested or based only on the microstructure characterization. But I think you showed some mechanical test, isn't it?
Yes. We are currently we work on fatigue test on this kind of material. And the first results are very promising compared to, for instance, the pieces obtained with powder technologies. With this kind of technologies based on powder materials, there is some positives that decrease the fatigue strength. And the first result on our material obtained with the WAM process shows there is a very good fatigue properties. So it seems very promising, but it's just the beginning of this mechanical characterization.
Thank you. That's a good observation. He's not here from colleague here, Christian. He noticed that in your presentation, in the fatigue analysis, you show one test with an inertized tensile and one with oxidized sample, in the fatigue test. And we noticed that the limits were inverted between the horizontal and the vertical samples, between the oxidized and the inertized. The results were inverted in horizontal and vertical samples, the results. How do you explain that? When it was oxidized, it was more, the limit of fatigue was bigger for the oxidized in horizontal than in vertical. Yeah. Do you have an explanation for that, or?
Yeah.
What do you think that happened there?
Yes, it's these results.
Yeah,
this is very new. It's the new results. So yes, there is a change in behavior on the oxidized samples. We doesn't explain that today for the moment. The oxidized samples, these samples were built using the WAM process with a bad protection. So we call oxidized samples, but it's samples manufacturing with a lesser a bad protection against oxidation. So maybe there is a modification of the microstructure. There is some oxide inside. It's with the surface of each layer is oxidized, and when a new layer is deposited, the oxide stays inside. There is an effect of the oxide probably, but this inversion, for the moment, we can't explain. We have no explanation for this inversion.
Don't worry, thank you.
No problem.
We have another question from Emmanuel again. Do you know if in the simulations your team are doing, they are considering the birth and the death of the elements. It means if they are considering the addition of finite elements in the simulation. If the elements are appearing or disappearing during the simulation, like an additive process. Do you are having these considerations or not yet?
We have it's not our work, but we are working with partners. We are working with other partners, other lab partners in France, specialized on the numerical simulation, and they have many strategies to model the by finite element. And one is to activate the element layer by layer, or a group of layer by layer. It depends of the scale of the modeling. There is modeling at the scale of the well pool to predict the microstructures, and there is also some simulation at the scale of the component to predict the residual stresses and the distortions, and for the simulation at the size of at the scale of the components, they activate the elements by a group of layers to decrease the computation time.
Okay. I think we are working in our team. We're working in something similar. I think we can collaborate maybe in that.
Yes.
Another question. Do you have a special strategy for multi-layer deposits for oxygen highly reagents like titanium or aluminum alloys? I think he's asking about how do you are protecting your deposits for titanium, aluminum, I think so. You have something special, a fixture or something that you did?
For the aluminum, we have no problem, because thanks to the arc process, the oxide layer that forms in the surface is eliminated thanks to the electrical arc. So there is no problem with aluminum alloys concerning the oxidation. With titanium, it's a real problem. We have no solution. The only solution is to create an inert atmosphere around the building piece. So we work on chambers around the manufactured samples to protect against the oxidation. But with titanium, it's a real issue, the content of residual oxygen.
Okay, perfect. I think that's a problem that everyone working with titanium is having. Here we are working in that too. Okay. Maybe we can exchange some ideas. I have some other questions. The optimizations or the problems you have found in the form of the deposits, they are independent of the materials, or you have the same problems in all the materials?
Concerning the building strategy?
Yeah, the problems, the optimization of the deposit, like the formation of the bit, the gate bit at the beginning,
yes.
or the humping, something like that.
Yes, it depends on the materials. It's a problem, especially with aluminum alloys. With steel deposit or stainless steel deposit, we have now the same problem. Yes, especially with aluminum alloys.
Okay, thank you. Well, I don't have more questions. I don't know if something that you're still listening to us have another question, this is your last opportunity today. But if not, thank you so much, Fred. Have some time. Yeah, I think. We are really happy for your presentation, your participation in our small virtual Congress. And we hope we will have more exchange like this, and that we have the opportunity to collaborate in a moment. As I told you, here in Mexico and in America, in Latin America, we are working a lot in IT manufacturing, and I think the one process is one of the most interesting for us too. Well, I think we have to keep communication about those topics, and I hope we can work in the future. I don't know if you have something to add.
Oh, no, it's okay. Thank you very much again for your invitation. It was a pleasure.
Okay.
Frederick, thank you so much again. Hope we can see you again soon.
Thank you.
Have a nice day. Para toda la gente que sigue conectada, les recordamos que nuestra siguiente transmisión empieza a las 11:30 con la plática del doctor Raimundo Arroyave. Vamos a mantener la sesión abierta por si quieren quedarse conectados. No vamos a finalizar esta sesión. Muchas gracias. Buenos días a todos. Bienvenidos nuevamente a nuestro segundo día del ciclo de conferencias virtuales ADITIVA Querétaro 2020. A continuación tenemos la conferencia del doctor Raimundo Arroyave. El doctor Arroyave obtuvo su doctorado en Ciencias de Materiales en 2004 en el MIT. Después de su postdoctorado en Penn State, se unió al Departamento de Ingeniería Mecánica de la Universidad de Texas A&M en 2006. Actualmente es profesor en el Departamento de Ciencia e Ingeniería de Materiales. El área de especialización del doctor Arroyave es el campo de la ciencia de los materiales computacionales, con énfasis en la termodinámica computacional y la cinética de los materiales. Él y su grupo utilizan diferentes técnicas a través de múltiples escalas para predecir y comprender el comportamiento de los materiales inorgánicos, aleaciones metálicas y cerámicas. Las técnicas van desde los métodos AB infinito, la dinámica molecular clásica, la termodinámica computacional, así como las simulaciones de campo de fase. El grupo del doctor Arroyave se ha centrado recientemente en la simulación y en el descubrimiento y diseño de materiales basados en datos en una amplia gama de contextos, incluyendo la fabricación aditiva. El doctor Arroyave ha sido coautor de más de 175 publicaciones en revistas revisadas por expertos, 20 actas de conferencias, así como cerca de 120 ponencias y 75 charlas invitadas en los Estados Unidos y en el extranjero. Ha recibido varios premios internacionales y nacionales. Tiene una designación de nivel 3 del SNI por el CONACYT a partir del 2017. Muchas gracias, doctor Arroyave, por acompañarnos. Le cedo la palabra.
Gracias, ¿me pueden oír?
Sí, lo escuchamos perfecto.
Muy bien, mi plática va a ser en inglés, pero primero les quiero agradecer a todos por la invitación en español. Conozco a la gente de CIDESI desde hace muchos años. Me ayudaron mucho cuando organicé la conferencia CALFA en Querétaro en el 2018. Y a Juan lo conozco desde que era estudiante y yo estaba empezando como profesor hace muchísimos años, ¿no? Entonces, me da mucho gusto estar aquí. Me da mucho gusto ver lo que están haciendo en cuanto al Centro de Manufactura Aditiva en México. Pienso que es una cosa muy, muy buena y por lo que veo están a la par con los mejores centros que he visto aquí en Estados Unidos y en otras partes. Entonces, de mi parte, felicidades y voy a empezar a compartir mi pantalla ¿Lo pueden
Muchas
ver?
gracias. Sí, la vemos perfecto. Muchas
Okay.
gracias. Bienvenido.
Okay, so today, now I'm going to switch to English. Today I'm going to talk about towards 3D plus printing. And what I mean by 3D plus is, going beyond the many benefits that, additive manufacturing or 3D printing has currently as used in industry. And, maybe try to think a little bit outside the box and take advantage of what additive manufacturing can do to do things that would be absolutely impossible to create with other manufacturing technologies. So I would like to thank many funding agencies because through their funding, we have been doing all this work, including the Army Research Office, the National Science Foundation, NASA, Department of Energy, and many other agencies. And I would also like to highlight the collaboration that I have had with the groups of Ala Elwani, Ibrahim Karaman, and Rich Malak. And actually, what I'm going to present today is the result of very strong collaborations with these three research groups. Because the type of work that we're doing requires the expertise of many people in many different areas. Okay, so I will apologize beforehand because I will talk a little bit about. Just give me a sec. I will talk a little bit about general concepts in additive manufacturing, even though the conference itself is on additive manufacturing, so you are already familiar with many of the very basic concepts that I'm going to talk about. But this talk is really self-contained, and I provide this background to provide the proper context for and the motivation for what I'm going to talk about. Going beyond 3D printing. To talk about 4D printing and compositionally graded or functionally graded materials. And then I will briefly conclude and put forward some potential future research areas. So, as you all know, additive manufacturing is a process for building a 3D solid object of arbitrary shape and complexity from a digital process. And in this case, AM uses an additive process where the materials are deposited or added on a layer by layer basis. There is work already, and I think that, for example, groups at Lawrence Livermore are working on voxel level printing. So they, instead of printing on a layer by layer basis, they actually print in volumes, and that is very exciting. Research. It almost looks like science fiction, but it's not really applicable to metals. And it can only be applied to some very specific materials, but the future is here. If you have a chance to go to Lawrence Livermore National Lab website and see what they're doing with 3D printing, they're doing outstanding work. Now, AM is distinguished from subtractive manufacturing because the latter requires the removal of material. And of course, when you're doing subtractive manufacturing, you are limited in the type of shapes that you can create, because sometimes there are internal features of the part that cannot be machined using traditional manufacturing processes. So additive manufacturing has evolved from rapid prototyping to widespread use in some industries. So since the 90s, actually, when I was at MIT, they were talking about, rapid prototyping. Some of the earliest printers were developed, or they were used at MIT, in the late 80s and early 90s. Actually, my advisor, one of his students did one of the first e-beam printing of Inconel back in 1997, 1996, if I'm not mistaken. So additive manufacturing has been having increased industry relevance and deployment in a wide range of applications. And it is actually posed to be a dominant manufacturing approach in the near future. And there are different areas of application where the level of maturity is really high. So for example, somewhere I read that in the future, all dental parts are gonna be 3D printed. I don't know if they're being done by this method now, all of them, but in the near future, 100% of dental prostheses are going to be done with 3D printing. And I'm sure that the same thing is going to happen with more industries as the case for additive, becomes stronger, because they can either do things that otherwise would be impossible, or different additive techniques have been reaching or could reach economies of scale, etc. Okay, so there are many benefits to additive manufacturing. I think that one of the most important benefits is the fact that engineering design becomes more efficient. That is, you can, by doing proper topology optimization, you can actually cut a lot of redundancy in your design to actually make things that otherwise would be very difficult to make with other techniques that save a lot of weight, because they save a lot of material. You're only using material to carry load when you need it, for example. The other advantage of additive manufacturing is part consolidation. So if you can fabricate a part of complex geometries, that means that you don't need to connect as many parts using, joining techniques or fastening, etc. And this brings a lot of benefits, including a reduction in the inventory if you have a maintenance shop, simplification of the design specifications, control over the parts in a big system, and so on. Another advantage of AM is that perhaps this is one of the major advantages, is the fact that with AM, additional complexity comes mostly free. So it is actually possible to fabricate components that otherwise would be impossible to fabricate with other techniques. And the cost associated with increased complexity is marginal relative to the benefit of having this complexity, right? So for example, if you 3D print a jet engine blade, you can actually potentially print, very complex and efficient internal cooling channels that would be extremely difficult to produce via casting, for example. Okay. Another benefit of AM is the fact that you can do mass customization. And by mass customization, I mean you can create and print objects and parts that are specifically made for a particular application, and you can make many of them. So you can, for example, this is extremely important in in biomedical applications where you actually have to print prosthesis to replace bone, for example. Everybody has different configuration in their bone structure. So in principle, you would actually need custom-made 3D printed, bone replacement parts, right? You couldn't do this practically with other manufacturing techniques, but with machine learning, that is, entirely possible to do. There are a number of additive manufacturing technologies depending on the material class and the throughput and so on. Here I have just a list of them, but every year there are, maybe a dozen or so new technologies that are being developed, and these are technologies that are being developed in all countries. So it is a very fast-moving area. Whatever we say now is going to become obsolete in a couple of years, but this is a representative list of different types of technologies related to additive manufacturing. The most commonly used ones, although in the morning we listened a talk on wire-based additive manufacturing, but the most commonly used ones by industry and the ones that are mostly investigated in a university setting are powder bed fusion and directed energy deposition. And I bring them up because these are the techniques that we are actually using, or these are the manufacturing technologies that we're using to do our work on 4D printing and functionally graded materials. So in the case of powder bed fusion, as you all know, you have a point heat source. And this heat source could be a laser or an electron beam. And this source selectively fuses or melts a region of the powder bed. And as the heat source scans a given layer, you create a geometry in that layer, and then you build a three-dimensional object by dispensing more powder, roll into layer, and then selectively melt or consolidate the powder using the the heat source. So this technique is widely used in industry, and as I said before, is probably one of the most commonly researched on in a university and a national lab setting. It is very slow. It tends to be very slow, so it's kind of difficult to scale up. But it is one of the most robust techniques to 3D print metals. The other very common, 3D printing technique is directed energy deposition. And in this case, what you do is you have, you basically feed both energy and mass into the substrate that you want to build into a three-dimensional part. And what you do is, by depositing either wire or powder at the same time that you are actually shining heat source on the substrate, excuse me, that you want to build, you create a melt pool that then solidifies, and you start building, on a layer, like the part on a layer by layer basis. DED tends to allow you to create parts at a higher rate, about a factor of 2 or even 5 relative to powder bed fusion. You add more energy to the parts, so you can alter the microstructure a lot more than what you would do with powder bed fusion. With DED, it's possible to print multiple materials at once, and this is an advantage that we use in our work in functionally graded materials. And in general, it's a widely used technique. It's actually used in industry significantly in the form of cladding. So when you need to do repairs of jet engine blades, a lot of the repairs are done with cladding, which is basically a form of directed energy deposition, to say so. Now, so in terms of benefits for additive manufacturing, we have the fact that you can create very geometrically complex parts that otherwise would be impossible to make. You have flexibility in the design, and you can actually do mass customization. You can do part consolidation to eliminate problems of inventory and to make your specification of the design of a component or a system more simple. And of course, you have the advantage of saving material and saving weight by truly optimizing the shape. So you only use the material where you need to carry load, okay? Now, the question here is, can 3D printing actually do more than that? Now, if we look at synthetic materials, they are kind of primitive. They're monolithic. They don't have a lot of hierarchies to them, and they are really limited by the manufacturing process. So, the standard forms that people in industry use to make, things that are more complicated are rods, bars, plates. And from these, design primitives, people then do bending, welding, joining, drawing, etc., to try to make more complicated parts. But if you look at them, most of materials are really, like, synthetic materials tend to be boring in the sense that even when you're talking about architected materials that have, some, macro structure beyond the microstructure, these motifs tend to be regular and they repeat themselves in three-dimensional space. So this is how materials of the 21st century, most of them look, at least the materials that we use to build, things that are macroscopically observable. 2D materials and nanomaterials and so on may be more complicated. But even in those cases, we don't have the technologies right now to create very complex, hierarchies in space. On the other hand, if you look at natural materials, if you look at bone, for example, it has, a wide range of scales, and each scale is configured in a very specific way to maximize load carrying at the same time of, minimizing weight, for example. There are other types of biomaterials, for example, the mantis sheep claw, that is extremely tough, is made with the same, long chain protein, but this protein, it is arranged in many different hierarchies of scale in a very interesting way, to produce extremely tough, structures. And if you look at all kinds of different biomaterials, you see that they are extremely complex, extremely hierarchical, very efficient, right? And this is something that we don't have in nature, right? So we cannot engineer, a meta material or an architecture material to have more than a couple of scales at most, right? So the question now is, can we actually go beyond shape complexity in the context of additive manufacturing, right? So the current value proposition of AM is highly customizable products with complex shapes that either make the design process more efficient or enable designs that otherwise would be impossible. Yet, these underlying 3D printing technologies could potentially be leveraged to achieve much more. And this is what I call 3D plus printing or beyond 3D printing. And in this talk, I'm going to talk specifically about things that we have done in my group in collaboration with my colleagues, Ala Elwani, Ibrahim Karaman, and Rich Malak, that have to do with 4D printing or functionally graded materials. So I'm going to talk a little bit first about what we're doing in 4D printing. Okay, so 4D printing, for those of you who are not familiar with this term, is basically about additively manufacture structures that can change their form, property, or function with time under stimulus, right? So you have a three-dimensional object, and this object is made with a material that responds to light or change in pH or temperature or magnetic field or stress. And when the material undergoes this change in structure or change in conformation, under this stimulus, it's going to change its configuration macroscopically, and that means that you're going to have essentially something that changes shape with time. And of course, 4D printing expands the potential of 3D printing by providing more degrees of freedom to engineering design. And here we have, this is probably the first and most famous paper on 4D printing by Tibbits, at MIT. And they made this object out of a shape memory polymer. And by doing a very clever way, organizing a very clever way, the design and the fabrication of this polymer, they were able to create objects that change shape as soon as you change the stimulus. And I must be frank, I don't remember what change in stimulus was here. Probably was pH or temperature or something like that. But this was a very interesting demonstration of the concept of 4D printing. So this is a relatively new concept. This paper was published in 7 years ago. But now there has been a lot of activity in all fronts trying to explore 4D printing. So to date, 4D printing has mostly exploited stimulus-responsive soft materials, right? So these are polymers or liquid crystals and so on. And you can see here many different applications, from origami, that is objects that start with a two-dimensional conformation and then arrange themselves into a three-dimensional shape. Smart packaging, meta materials, they have been used in biomedicine, tissue engineering, smart devices, and so on. The type of materials could be, single, shape memory polymer, shape memory polymer composites, multi-materials, etc. The type of stimulus go from, photo stimulus to thermal, temperature, water, pH, chemistry, magnetic field in the case of shape memory polymers that have embedded magnetic particles. And there are a wide range of techniques that have been used to print these objects. Okay, so most of these materials, these stimulus responsive soft materials, have been shape memory polymers, which are polymers that undergo reversible shape changes or conformation changes when you apply different types of stimulus. And there's a lot of activity on shape memory polymers around the world. And I think that in the context of shape memory polymers, 4D printing is perhaps one of the most interesting technologies that has increased the potential of shape memory polymers dramatically. Okay, now what about metals? So I mentioned shape memory polymers. In metals, we have something called shape memory alloys. And these are, metallic alloys that undergo large recoverable strains as a result of reversible martensitic transformations. Martensitic transformations are transformations that are not diffusive. In this case, what happens is you have a crystal structure, you have a martensite, and then when you increase the temperature, you go to austenite. So you have only lattice level changes in the structure. You change the crystal symmetry of the structure, right? And these transformations are reversible. Okay, so that means that you can go back and forth between one state and the other state. And these transformations can be triggered by stress, temperature, magnetic field, excuse me, or a combination. So, chain memory alloys have been known for the past 70 years. I think that the first one was discovered in the Naval Research Lab, which is nitinol, nickel titanium, in the 1950s. And since then, there has been a lot of research on chain memory alloys, and there has been some applications that have already been enabled with these materials. Okay, so these materials, and what makes them unique relative to chain memory polymers is the fact that they can withstand significant loads while carrying, while undergoing the transformation. This is, orders of magnitude. In many cases, it's orders of magnitude more load than what you can do with a chain memory polymer. They can withstand extreme environments. So there are, high temperature chain memory alloys that operate at temperatures that are way above the capability of any polymer material. So you can use chain memory alloys to actuate aerospace components, for example. Okay. And an interesting thing about chain memory alloys, and the reason why they work actually, is because these are materials that are on the verge of stability. They are barely stable, right? And this is why it's very easy, quote unquote, to move back and forth between one state and the other state. Okay. So these are, very, almost metastable materials, right? They are on the verge of instability. And any material that is almost unstable, or it becomes unstable under some conditions, may be very sensitive to chemistry or conformation. This applies to chain memory polymers as well. In the case of chain memory alloys, they are extremely sensitive to changes in chemistry, right? So for example, here I have a plot of the transformation temperature of nickel titanium. This is the nitinol alloy as a function of nickel amounts. And you can see how the transformation changes from, the transformation temperature changes from 340 Kelvin at, close to, 50% nickel. And then as soon as you go to 51% nickel, so you have changed the composition by less than, 1 atomic percent, and the transformation changes by 140 degrees Kelvin, right? So this is an extreme sensitivity to composition. There are alloys like nickel titanium hafnium where this change occurs in a span of, is like 3 times or 4 times larger. You can change the transformation temperature by 500 Kelvin by changing the composition by 1 atomic percent. Okay. The same thing applies to microstructure. Here on the right side, I have a contour plot of transformation temperatures as a function of aging temperature and aging time. So this particular alloy undergoes a precipitation reaction. So you have precipitates that come out of solution, and depending on the amount of precipitates and their shape, you can actually change the transformation temperature dramatically by just controlling, the heat treatment, right? So clearly, these alloys are very dependent on composition and microstructure. And a key insight, and actually when we started thinking about this idea about 4 years ago, we said, well, if these alloys are very sensitive to small changes in microstructure and in chemistry, maybe we can use, we can control the additive manufacturing process to achieve location-specific behavior, right? So our insight was, if we know what levers to move in the additive manufacturing process, we may be able to change chemistry or microstructure or something, and we may actually see, some dramatic change in the behavior of, 3D printed chain memory alloys. Okay, so what we did was to combine 4D printing with functionally grading. So functionally grading is about grading or locally changing the special properties of monolithic structures. And 4D printing is basically printing with materials that are active. So we combine these two concepts, and I think that you can see this. This is one example of what we achieved. This is a hand where every finger was printed with different process conditions. It was the same chemistry, so we didn't change the chemistry here. We just changed the processing conditions. And in this case, I think that the only thing that we changed was hatch spacing. So we used the same power and speed. The thing that we modified locally was excuse me, hatch spacing. And we can see in this video how different fingers actuate at different temperatures. We are heating the container. This is glycerin, it's not water, because water would actually boil and you would have a lot of bubbles. We wanted to eliminate bubbles in order to see the actuation of the hand. But you can see that every finger is moving at is actuating at different temperatures. So there's a potential here, right? So we could create potentially a monolithic part that would act like a robotic material where you could have grips, or you could have different actuations at different temperatures by just controlling the conditions in which you print different elements of the part, right? So with metal additive manufacturing of materials that are very sensitive to changes in chemistry and microstructure, you can actually do 4D printing of metals. Now the question is, what type of things go on or happen when you 3D print these metals that changes their behavior in such a dramatic way? And this is just a still of the action sequence, so you can see the dramatic change in conformation that goes on when we heat up this 3D printed hand. So what we envision here is to look at materials as devices through 4D printing, okay? And what we want to do is to specially tailor additive manufacturing so we can have robotic materials in which the hierarchy, multifunctionality, and location specificity are considered concurrently during the design process, okay? So we know that this happens because we were able to do it, but that doesn't mean that we understand how to do it. And that doesn't mean yet that we can actually design 4D printing components, right? So the fact that we know, that 4D printing works in the case of metals doesn't mean that we are equipped yet to actually design 4D printed objects, okay? So the essential elements to make 4D printing possible are composition control. So we could potentially use DED to, deposit alloys with slightly different compositions, or we can exploit the fact that different elements actually have different vapor pressures. And, you may be able to, you probably are familiar with this problem in additive manufacturing. The final composition doesn't mate, or it doesn't match the initial composition of the alloys, because if the elements have a lot of, a very large difference in the vapor pressure, you are going to evaporate, some elements more than others, and that changes the chemical makeup of the part. That could be a problem, but it could also be something that you can use to your advantage, particularly when materials are very sensitive to changes in composition. And of course, you can also control the local microstructure, and with that, you can control, microstructural processes that change the transformation behavior of these materials. So what we want to do, and we haven't achieved, this is a steal from a proposal that we wrote that wasn't funded, but we're trying again, where the idea is to actually go and do some topology and shape optimization, then figure out what type of chemistry changes you have to achieve to get a particular shape memory response. We then proceed to do process optimization. That is, for a particular alloy, we want to figure out what is the region in which we can print parts without defects. And we want to do this within a robust framework to make sure that we can do this in a repeatable way. Okay. So there are many things here that we haven't been able to do because we haven't had the funding to do them yet. although we are, we're building pieces of the puzzle, we don't have the entire framework yet. But there are some things that we have done already. For example, process optimization. In collaboration with my colleagues, Ala Elwani and Ibrahim Karaman, we developed a very simple recipe based on the combined use of thermal models and machine learning frameworks with statistical calibration and so on, to rapidly identify the printable region in a particular alloy class, okay? So we have a thermal model, we predict an initial printability map, we carry out single track experiments, we calibrate the models. Now that we have models that are calibrated, we revise the printability map, right? To figure out where are the regions where you are more prone to keyholing or lack of fusion or balling in the case of powder bed fusion. And then we print, this white region is the good region. We print parts in this good region, and then we carry out characterization, of the, printed, tensile specimens. In the case of nickel titanium, this is how it works. We found the printable region. We then printed some, elements, some, coupons in these different, printing conditions. And then we were able to verify that they had no porosity and, had good, super elastic behavior. Now, so we know how to find the sweet spot in processing space. So then we can do, for example, tailor of the process conditions to do for the printing. But to do that, you actually need to build a lot of computational tools. It is not sufficient to just do experiments, because there are many things that you can change at the same time when you're doing 3D printing. And even though modeling is not perfect and there are a lot of uncertainties when we're using computational tools, they are not completely wrong, and they can potentially be used to try to build predictive models that tells us what happens when you change some conditions, to the chemistry or the microstructure of the material that we're interested in, okay? So what we want is to build a framework for the predictive analytics for additive manufacturing, where every single aspect of the fabrication process is going to have a computational, tool to look at it, but also it's going to have an experimental counterpart that we can use to verify and calibrate the models that we use. And just to give you an example, this is the first step. This is work that has been recently finished by one of my students. We are about to publish it. So we have a model, a thermal model that was developed by the Air Force Research Lab that allows us to predict the local thermal histories as you scan a part. And then, when you have these thermal histories, we go from these thermal histories to a model that takes into account the thermal history and the chemistry to account for the differential evaporation. And of course, this thermal model is calibrated using experiments. So once we calibrate the model, we use it to predict, the differential evaporation in, a given material for different processing conditions. Then we try to expand this in a multi-layer model to take into account, building, the model, the different layers into a part. And we have actually verified the model. It turns out that, as I said before, nickel titanium is very insensitive to changes in composition in this region, but very sensitive here. So what we did was we printed coupons with different processing conditions, and then we measured the transformation temperature using DSC. So, it turns out that measuring chemistry is very uncertain. So the uncertainty in WDS is plus minus 0.5%. And here we have a change of a fraction of that, and you can see how much the transformation temperature has changed. So instead of doing chemistry or doing analytics to find the chemistry, we actually measure the transformation temperatures, which we think is a more precise way of measuring indirectly the chemistry, at least in this region. And then we compare with the results of the model, okay? And I must confess here that we didn't do any calibration of the differential evaporation model. The only calibration step that we did was of the thermal model, but once it was calibrated, everything else was a prediction from first principles. And we found extremely good agreement. It turns out that the error in our prediction is 0.15 atomic percent, which is several times less than the uncertainty that you get when you do measurements of chemistry in WDS or EDS. Okay, so this is just one step in the process. Actually, that will be the second step. The first step will be the process optimization here. Okay, the second step or the third step will be exploring differential evaporation, and by using different parameters like power and velocity or head spacing, we can potentially arrive at different chemistries and different transformation temperatures. Okay, but the missing step, what we haven't done yet, is to actually integrate the process optimization and the materials modeling part with an engineering shape or topology optimization to try to start doing 4D printing. Okay, now of course 4D printing has been demonstrated in a large number of applications, and this is a graph that measures kind of like the hype of new technologies. So we are here in 4D printing. We are triggering a lot of innovation. We're gonna reach at some point the peak of hype. Right now, deep learning, for example, is at the peak of hype. What happens in a lot of technologies is that once you reach this peak of hype, eventually you come down to earth, right? And then you develop technologies slowly on a step-by-step basis. For example, facial recognition was here maybe 15 years ago. Then 5 years ago or 6 years ago it was here, and now with artificial intelligence and machine learning and all these type of techniques, now it's very easy for you to say, well, I'm going to look for pictures of my grandma by just having Google recognize my grandma's picture in my photo album and have Google find all the pictures that have my grandma so I can remember her, right? So this was science fiction 20 years ago. Now this is like, we don't even think about it. It's a feature that our iPhone has, or what other phone system you use. And now it's a technology that is matured, it's improved incrementally. It's not a quantum leap every year, right? But it's improved in a regular pace. We are in 4D printing, we are here. 3D printing, we are probably here in this region. But in 4D printing, much remains to be understood, and considerable development is needed. But if it's possible, we can do a lot of really cool things that would expand the things that we can do with engineering. Okay, so this is the first part of my talk. I think I'm almost on time. I may be running a bit late, but I think I will be able to finish on time. Now I'm going to talk about functionally graded materials. So this is another expansion of 3D printing that is made possible by additive manufacturing technologies. Okay, so the research vision is to actually create a computational methodology to design compositionally graded alloys with an arbitrary number of constituent elements that satisfy specified constraints and optimize design objectives. So what we actually want to do is to, now that you can do topology optimization, wouldn't it be cool to actually change the properties of different parts of this already topology optimized component to improve its performance, right? Maybe this part is facing very high temperature, so you need a temperature resistant material here, and here you have to withstand a lot of load, so you may need a very strong material here. There's no reason why, if you're already doing this topology optimization, why don't we actually change the properties locally of this geometrically complex part? Okay, now there are gaps. In the case of metals, for example, linear gradients do not work, and the reason why they don't work is because whenever you try to connect two points in a composition space, it is very likely that if you connect them with a straight path, you're going to find faces that are detrimental, that are going to make the part brittle. And also, design methods are very limited. There are no design techniques to use if we want to actually do this. Okay, so functionally graded materials are known as materials that change properties along special dimensions, and they're usually used to achieve contradictory performance requirements. For example, lightweighting, as I said before, with high temperature performance. There are already there's a lot of work on functionally graded materials. blended polymers, metal matrix composites, and so on. The bone itself is functionally graded, right? So the bone changes density, for example, as you move from the very center to the outer parts of the bone, and you change that, or the bone changes density to carry the load more efficiently, okay? So we can do functionally graded or compositionally graded alloys with DED. The only thing that we need to do is to use a DED that actually has multiple powder feeds, right? So we can, potentially change, the feeding rate of different compositions or the different, powder, sources. And if we change them gradually, we can actually change things, change the composition in a gradual way. The problem, however, as I said before, is that you may actually have, brittle secondary phases, or you may actually have undesirable properties that can prevent manufacturing or diminish performance, okay? So the previous design methods, and this is kind of like a new, well, it's not that new anymore, but the first papers on compositionally graded alloys were published in 2014. Most attempts have failed because if you want to do these paths in a linear way, most of the time you're going to encounter things that are, brittle, so your part is going to be brittle. But there have been many, approaches. Most of them are very primitive, and they don't really allow you to design with multiple components at the same time, okay? So what we thought of doing in this case was to actually treat the problem as that of motion planning. We imagine that we have a beginning and an end, and then we thought of looking at the composition, at each composition as a robot that needs to find its way in a multidimensional space in order to avoid some obstacles or satisfy some constraints, okay? So essentially, we mapped the problem of functionally grading as that of motion planning or robotic path planning. And the idea was we are trying to go from this point to this point. We're going to try to avoid some obstacles, and we're going to try to make sure that we optimize a particular cost function. This cost function could be cost of the material. It could be the length of the path, etc. Right? So the idea was, can we actually map this design problem to a motion planning problem? And if that is the case, how to build the algorithm to do it, right? So what we did was, the first approach was to actually use computational thermodynamics techniques to sample the thermodynamic space, then use a classifier to classify regions that were obstacles that were not interesting to us, and then use a path planning algorithm to find an optimal path that would take you from one point to the other, in a way that is automatic and that you don't need, to do a lot of, hand calculations or experiments, okay? There are many different types of path planning algorithms. You can use neural networks. You can use traditional optimization. You can use graph search. Graph search is basically used for mapping applications like Google Maps or Apple Maps or Waze or any other type of mapping technology. We decided to use, instead of these methods, sample-based planners because they are probably guaranteed to work, and they need less memory and less training data than other techniques. Okay. So specifically, we use something called rapidly exploring random tree. And this rapidly exploring random tree is a path planning algorithm that allows you to explore or find paths in multiple dimensions. Okay. But in this, for this algorithm to work, we actually have to provide models for the obstacles and to calculate the cost of a particular path. Okay, and I will not go into detail into how this path works, but you're basically sampling, this multidimensional space in order to find a viable solution. And once you find the path that connects, the initial and the endpoints, then you can optimize around that path, to minimize a particular cost or maximize a performance metric, etc. Okay, so the constraints are hard requirements in terms of the state space. That is, things that you don't want to see in your path. So what we do is, we do some, we use some sampling schemes, to try to figure out, and in particular, we use surrogate models, classification in particular, to try to, tell the path planner, don't go there, avoid this, region, this is an obstacle. So we could actually guide the path in, an effective way. So the objectives could be, for example, minimize the path length, clear the obstacle with a distance, or to optimize a particular property or performance. Okay. Now, deleterious phases are, limiting functionally graded compositions. This is a review, and in this review, it turns out that most attempts to do compositional gradient fail because you precipitate these detrimental phases that are, extremely damaging to the structural integrity of the part. Okay, so one of, the main objectives was to actually verify that we could avoid obstacles by using our path planning framework. So this is just one example. We have done many since then. In this case, we actually tried, to find a path between steel to chromium. So this is a, 316 stainless steel. It's an iron nickel chromium alloy to pure chromium. And, we considered that we didn't want to see chromium nickel 2 and sigma phase. We consider that those two phases are, deleterious. And, the task was to find a path that could actually clear those, obstacles at all temperatures and, be free of cracks if we were able to build it, right? So this is what we did. This is what you get in a linear path. And this is, what you can get if you plan the path. And, then we did the experiment with a multi-material DED. It turns out that it is very difficult to do multi-material printing. You actually have to calibrate the feeding rate and, test it and validate your calibration curves significantly. And this was the first attempt. Now we are getting better at, calibrating the feed rates of the multi-material printer. And we can get within 1 to 2 atomic percent in terms of the composition that we want to print versus the composition that we actually print. And this is just a demonstration. The linear gradients has a lot of sigma phase. The plan gradient, on the other hand, we didn't observe any cracking. No sigma phase after we do heat treatment, as you can see here. So here we only have, the alpha ferrite phase. Now, prior work, by us was only minimizing the path length or maximize the separation from obstacles, but there are problems with properties. For example, if you plot the thermal expansion coefficient of this path going from steel to pure chromium, it turns out that there are, the thermal expansion coefficient changes by a lot as, you move in the path, and changes in thermal expansion coefficient and discontinuities in the thermal expansion coefficient can lead to thermal stress concentrations, and that can, compromise the integrity of the part. So the question was, can we actually do something to try to minimize these drastic changes in properties while at the same time avoiding detrimental obstacles? So essentially what we wanted to do is to try to find ways of printing a path that avoided obstacles, but also that ensure that properties change monotonic. And monotonic means that, the change is always in one direction. So as you move in the path, you cannot go up and down in a particular property value. The idea is that you actually go down or up as you move in, along the path. And it turns out that there is something called monotonicity index, and it is very interesting that metric was used, and my student actually found this paper in a journal of economics. So there were two economists who were looking at some particular change in an economic variable over time, and they wanted to actually measure where this change was monotonic or not, and they created this monotonic metric. And we're using, in our work, this monotonic metric that was used for the first time, as far as we know, in an economics context to do path planning for compositionally graded materials. Now, one of the cool things about this, finding this monotonic path is that once we find a path that is monotonic, by controlling the deposition rate, we can actually get non-monotonic paths, right? So this is something really cool. We haven't demonstrated it yet, but we know that it works, and we just have to put some effort to actually do it. Once we find a path that is monotonic, we can write an arbitrary property profile, right? So I can write a thermal expansion coefficient that changes sinusoidally or that changes with a square pattern or whatever, as long as the limits in the property are bounded by the path. And this transformation can be done. So I can transform this path to this path by just changing the deposition rate, changing by how much I deposit different powders. Okay. So what we did was we looked at the iron, cobalt, chromium system. And the question was, can we actually find a path between this initial point and this goal point, minimize the obstacles, so avoid the sigma phase, and at the same time, minimize or make the change in thermal expansion coefficient monotonic. Okay, so when we find the shortest path that avoids the sigma phase, this is what we get. We have a non-monotonic change in the thermal expansion coefficient, and this change could lead to dramatic changes in thermal strengths, and that can result in cracking of the part. This is the algorithm working in real time. Well, not in real time, but it's you can see how it's working step by step. We are finding a path that avoids obstacles, and at the same time, we are moving in composition to make sure that the thermal expansion coefficient changes monotonically. And you can see that this path is definitely not the shortest path. We actually have to went away from the sigma phase, right, and then move back along this line and connect to this point in order to make sure that the property gradient was monotonic. And this is a dramatic change in behavior between the non-monotonic thermal expansion coefficient profile and the monotonic one. So we know that we can do this, right? We have been able to do it for this particular property. But if you have property models that can predict the behavior of a material as a function of composition and microstructure, and you can predict the composition and microstructure as a function of path, you can use this framework to do property writing in a way that otherwise would be impossible. Okay, so the future work that we have for our working functionally graded materials is process planning. So it turns out that processing of compositional gradients is extremely challenging, because if you change the chemistry, you change the thermophysical properties, and if you change the thermophysical properties, you change the physics of printing. So in principle, every time that we change composition, we actually have to change potentially the processing conditions to make sure that we have always optimal processing conditions for every chemistry that we're trying to print. Okay. We can potentially use thermal models to produce printability maps. This is work that we have done for powder bed fusion, but we are actually working right now to build printability maps for DED. Okay, and the idea was to actually come up with post-process paths to predict optimal process parameters once we have a composition path. The other thing that we are working on, and this is work that is is more evolved now because this is just computational work, we're actually trying to do multi-material topology optimization, where we change not only the topology or the geometry of a part, but we also change the local chemistry and potentially the local microstructure to have tailored properties. So we're working on the mathematics and the computational work related to this. And actually, when I say we are working, it is my student who is working on this. He's really, really smart. And he's actually doing something that no one else has done yet. And we're very excited about his work. So in conclusion, and I'm finishing actually a little bit earlier than I thought, 3D printing is on the cusp of transforming entire industries. So it has transformed some industries already. And, every year there's an industry that is being transformed a little bit more by 3D printing. The major advantages of, 3D printing is the flexibility in the design, mass customization, and, the fact that you can create very complex shapes. Even more transformative technologies than 3D printing could be achieved by going beyond 3D printing, exploring the potential of AM to do local tailoring of chemistry, microstructure, property, and/or function. But, one of the challenges here is that if you want to do 4D printing, you have to have extremely sophisticated modeling techniques that allow you to model what is going to happen to the material when you change chemistry, when you change process conditions and chemistry and so on, right, in a very reliable way. So that is the forward problem. More difficult is the inverse problem. It turns out that sometimes these tools take a lot of computational time. If we want to design a path and we have all these physics-based models to help us, make predictions of what happens to a particular chemistry when you change the process conditions, if it takes too long, it's going to be quite expensive to design a path, right? So you either have to find more efficient ways of designing for 4D printing or functionally grading, or you have to find more efficient forward models, maybe with machine learning, neural networks, and so on, or you have to do a combination of both. Develop machine learning models that can emulate physics-based models at a fraction of the cost, and also use advanced engineering optimization tools to try to minimize the cost of optimizing, the design of these, 4D printed or compositionally, functionally graded materials. And with that, I would like to thank you for your attention, and I would be happy to entertain questions that you may have. Thank you very much.
Ok, muchísimas gracias, doctor Raimundo Arroyave, por tu presentación tan ilustrativa. Gracias por habernos hablado en un principio todo este resumen de la manufactura aditiva. Para aquellos que no habíamos atendido todas las conferencias, pues creo que fue bastante complementario. Y por también mostrarnos pues, el futuro realmente, hacia dónde podemos dirigirnos. Tenemos algunas preguntas de aquí. Algunas están en inglés, otras en español. No sé si la mayoría del público que nos atiende es audiencia que habla español, o tenemos algunos que hablen solo inglés. Pero, bueno, no sé cómo prefieras, si queremos responder en inglés, los hacemos en inglés. Es difícil.
Tal vez es mejor, para estar seguros, contestar en inglés.
Okay, perfecto.
En caso de que haya gente que no habla español.
Perfecto, entonces vamos a tratar de... Algunas están en inglés, algunas en español. Tal vez tratemos incluso traducir las que están en español, ¿no? Para tenerlas en inglés. Perfecto. So we are going to start with the questions. We are to make them in English to be sure that everyone is understanding. Well, first one is from Anonymous, because we don't have the name. But I think you didn't talk to us about DFT, but some of us know that you are working with that, you know the topic. So he's asking about the theoretical and computational tools such as DFT for the understanding of the behavior of this type of materials are used, how it describes the physics associated with the phenomenon. How do you do that?
Okay, so yeah, I mean, I think that, the question is about DFT used to understand, for example, active materials like shape memory alloys, right? It turns out that is very difficult to do because, shape memory alloy is an unstable material. It undergoes a phase transition. And, there are attempts to do first principles based prediction of the behavior of shape memory alloys. and we have done it in my group, and there are other groups that are doing it. It turns out that it's extremely difficult. We don't have the theoretical techniques yet to capture the dramatic change in properties with composition. So we can predict trends, but trends are not sufficient where you actually try to design. So if you want to know what is the transformation temperature of a chain memory alloy, is infinitely more, is infinitely cheaper, right, and more reliable to just make the alloy and then measure the transformation behavior. It is, I mean, we can get some insight into why the transformation temperature changes in a certain way using DFT, but it's extremely, qualitative, despite what people may say. It's not that reliable. You can use some techniques like this to build features that then you can use in machine learning models trained against experiments to try to build better predictors, right, of behavior. But it turns out that they are, these materials are extremely difficult to understand from a theoretical point of view. But we use other techniques and other computational methods that are more amenable, that are more controllable and understandable and simpler to implement, such as, thermal models, microstructure models, evaporation. We can use mechanics models to try to predict the stresses, the actuation behavior of chain memory alloys, and so on. Okay.
Thank you, Doctor. We have another question from Enrique. I think he's a researcher that works with us. First question is about, do you have some examples about the control in microstructure from the alloy nitro titanium using 4D printing? And in that case, you have some, do you know if they need some post treatments like heap or
yes, I mean,
something?
Yes, I mean, you can change the microstructure when you change the process conditions. If you change the thermal history, if you change the power, the speed, and so on, you definitely can change the microstructure. The most dramatic change is in composition, at least in nickel titanium, because it's very sensitive to composition. By just changing the hatch spacing, you can change the composition by 1 atomic percent, and that is sufficient to change the transformation temperature by 100 degrees. But you can also change the microstructure. For example, you can change the local cooling conditions so you have different precipitates. So yeah, it's possible to change the microstructure. With respect to heap, post-processing, yes. I mean, you can do post-processing, and sometimes you have to do post-processing if you have some defects or some microstructural features that you don't want to see in your material.
Thank you, perfect. Another question, I think he's interested in 4D printing or 4D constructions. And he's asking about if it is possible to fabricate alloys using only elemental powders.
So we haven't done this. We haven't done this for 4D printing, but we are doing this with DED, with multi-material printing. We can do that, and actually, we have a setup. We have a setup in our lab, in the lab of a collaborator that we call the Rapid Alloy Prototyper. So we can use a multi-material printer to print different alloys in a single plate. So then we can do high throughput characterization of those alloys. So we're going to try to do, alloy development. So it is possible to do local alloying with elemental powders, but we have done that only with our DED machine. When I talk about 4D printing, I always understand powder bed fusion, where you change locally the process conditions to have small, subtle changes in composition or microstructure that have dramatic changes in behavior. Okay.
Okay, thank you. Really interesting that. Okay, another long question from Álvaro Gómez. He says, the optimization calculations you have shown are used to determine the properties of the material from which the part is manufactured by additive manufacturing. Could those tools work to determine structural mechanical properties? And that's the first question. The second one, this is already thinking of cellular materials in which the properties depends not only of the material, but also on the architecture of the structure. What other mathematical tools could be applied?
So there's a lot of work on the design of metamaterials. I'm not an expert in metamaterials. There's a lot of people working on that. There are a lot of computational tools that people have developed to predict the behavior of metamaterials in the context of additive manufacturing. I came across a couple of papers, and actually, I think that I used a figure from one of those papers, when I was preparing this talk. The problem that you have, and actually one of the things that is extremely challenging is that, you can predict the properties of a metamaterial if you assume that the motifs of the metamaterial do not change, right? So, if you, for example, if you have trusses and thrust and so on, but that motif repeats itself, at infinity, right? You can probably build a representative volume element, right? Or an aggregate element or model for the behavior of that trust, and then just fill in your finite element model with the constitutive laws for that particular trust throughout the material, right? And that is fine, okay? People can do it. Now, if you change the configuration of the material, right? The chemistry and, the arrangement and the meta structure and so on a location by location basis, you cannot use a representative volume element anymore. You actually have to model the entire object with changing properties everywhere at the same time. That is extremely computationally expensive. You can do it, but first of all, imagine the amount of memory that you need, right? Because now you have to basically represent every single element of the part in a unique way. So you cannot basically use tricks to compress information, right? I think a colleague of mine calculated you may need like hundreds of gigabytes to represent a structure, digitally, right? Or more than that, right? And then you have to solve an elastic problem, and that is difficult. The plastic problem is even more difficult. Non-linear elastic plastic behavior is even more difficult to simulate, right? So, we may be able to do it, but the problem is that these models may be too difficult to evaluate, if you're trying to do design, because when you're trying to do design, you actually have to solve many forward problems, at the same time, right? So I think that here, one potential tool that can be used, a mathematical tool, would be machine learning, right? Maybe, you can train a neural network, right, to understand how to predict the behavior of metamaterials when you have different changes in the configuration, if you have enough data to train them, right? And it may be hard at the beginning because you may actually have to generate the data, but once you generate the data and you train the neural network, now you're going to have a neural network that can predict the behavior of a metamaterial where you change the local properties at will in milliseconds, as opposed to days or months or whatever, right? So potentially one approach to solve this problem is to use neural networks. And I'm sure that this is something that if nobody's doing it right now, there are going to be papers of someone attempting this tomorrow or, next month or whatever, right? It is actually, it's not trivial, right? But it's kind of like a natural thing to do, right? So I'm sure that people are training neural networks to design metamaterials now. And I'm sure that there are papers now where people have done it. I haven't found them because it's not my field. But if you Google right now and you say neural network, and metamaterial and design, I'm sure that you're going to have, I don't know, like 20 hits or so, whatever. People are doing this.
Yeah, thank you. It makes me think about, you talked to us about graded materials, and I have seen some graded metamaterials. I think it's something, exploring something similar, and maybe looking at the metamaterials, like the topological optimization you show us, maybe it could be a way to make a union between these. Looking this like a topological optimization, but maybe we can analyze the structure of the cellular of the lattice structure. Well, we go to the next question from Jose Mercado Rojas. He thank you for your presentation. He says you have an awesome research. He asked, in your work, the additive manufacturing process is avoiding some rayons by changing the powder composition. Could the path planing method be used as well with temperature control?
Yes, in principle, but that will be extremely more difficult to implement. So now, we're trying to do that. For example, there was a gradient that we were trying to print between an iron chromium alloy and tungsten for an application for plasma phasing components in a fusion reaction, nuclear fusion reactor that will never exist, right? Because nuclear fusion is always 50 years away, right? So nuclear fusion will never happen, although I shouldn't tell that to the people that gave me money to solve the problem. But in that application, for example, you have a plasma phasing component. You have a component that is facing a lot of heat, has to have a high melting point that is tungsten, and then you have to connect it to other components that can be welded to standard, nuclear type steels, right? And it turns out that in that one, we actually wanted to go from tungsten to iron chromium, and we had to go through a region that was pure chromium. The problem is that if we use the same process conditions to be able to melt tungsten, we boil chromium and we boil anything, right? Because tungsten has a very high melting point, right? So in principle, right, we actually want to, have high power when we make tungsten, and then we want to dial down the power as we are moving and, melting, material that have a lower melting point, right? It's not too easy. I mean, we can do it, but it's not too easy to control. I mean, right now, that's another problem, right? A lot of the 3D printers do not have open controls, so you can tailor with them, right? I mean, there are some open platforms now, particularly, I think that the powder fusion technologies the patents have expired now in many laser powder bed fusion technologies. And now that the patents have expired, there are a lot of institutions and companies that are building open platforms. Like Fraunhofer Institute in Germany is selling their open, powder bed fusion platform. There are other companies that are doing that. So for some technologies that are kind of older, as soon as the patent expires, people build open platforms that you can actually tailor and tweak and control and do whatever you want, and that is really cool, right? But some technologies, I mean, they're patented and they're closed, and the companies don't let you. I mean, if you actually go and try to control everything, your warranty is voided, and if something breaks, then you're on your own, right? So there are some practical limits to what we can do if we're using commercial technologies.
Perfect. Those are good news for us that make research. Well, from the anonymous one, we have more questions. He says that in the literature, machine learning has been combined with DFT for the study of the design of materials. And he asked, did you have implemented?
Yeah, we're doing some work on machine learning and DFT. Training neural networks to predict energies, predict the stability of materials. So we actually have used machine learning. We just published a paper where we use machine learning methods to try to predict the oxidation behavior of materials very easily, much faster than what you would do if you were to use DFT alone. So we can do prediction of the different oxides that form under different oxygen environments in contact with different materials using machine learning. So yes, we have used machine learning with DFT to do some predictions of materials and some alloy design.
Thank you. James Perez make us another question. What are the applications of these memory shape alloys and polymers?
I mean, there are many applications. For example, I don't know about shape memory polymers. It's not my field, but I understand that they're being used in the biomedical field quite a bit. Shape memory alloys are used in the aerospace industry. Actually, shape memory alloys are used in dentistry. So a lot of the braces that you use, I mean, the modern braces, they have, they connect each other with shape memory alloys because they can retain constant load on their, deformation, exploring the superelastic effect. They are used, shape memory alloys are used for passive active thermal controllers. They are used in aerospace applications where you actually want to deploy things in space. You can deploy them with, shape memory alloys. There's a lot of work on aerospace applications. Actually, colleagues of mine are being funded by the Department of Defense in the United States to build hypersonic materials or hypersonic vehicles. These are vehicles that go beyond Mach 1. I mean, they go to Mach 7, 8, and so on. And the problem with these vehicles is that depending on the Mach or the velocity that they have, they ideally would like to change the configuration, right? The angle of attack or something in the material, in the wing of the aerospace of the hypersonic vehicle. So people are using or are thinking of using shape memory alloys to change the conformation of aerospace vehicles so they are optimized for flight conditions that change over the mission of the vehicle. Okay, so there are many applications for shape memory alloys. They are not widely used. They have always been fascinating from the point of view of the science of of what you can understand about them. They are not super widely used, but they are used. Oh, there's another application, and we're working on that. It turns out that shape memory alloys undergo phase transformations, and these transformations carry a latent heat. Okay, so we are exploring the use of shape memory alloys as active thermal materials. For example, now with electronics, right? You are pumping so much current through a device that you need to cool it really fast. And you can use phase change materials that undergo a phase change to cool, the device. And one of those phase change materials is, shape memory alloys. And they tend to have very good properties as, phase change materials for sure. And those are just some of the properties of shape memory alloys or some of the applications of shape memory alloys that I know of.
Thank you so much for your answer. I think we have read all the questions. I want to thank you for your participation. This is a really, really interesting topic. I think there are many people interested in this, but you have answered many of our questions. I don't know if you want to add something, some comments. Where can we find your work?
So I have a website, but my website isn't updated. I mean, it's too hard to update the website. My website is old. I mean, if you want to see the latest work that we have in my group, you look at our papers, in Google Scholar. This is where we have, you will see all the papers that we have published. As I said before, this is not my own work. This is a very hard problem, right? There's no single group that can solve this problem. It's too difficult, right? And I have a computational group, right? So we don't have experimental facilities, right? So what I present is not my work, is a work that we have done in collaboration with 3 other groups. And it's the work that has been done by students, right? It's not done by the professors. We get to show our work and so on, but the ones that do the work are the students. So my message to all the students is, just work hard. Additive manufacturing is the future. is the past, the present, and the future. Actually, additive manufacturing, I think that it has revived metals research in the US. I don't know in Mexico or Europe, Germany or France or whatever, but I think that in the US, additive manufacturing has significantly revived the research on metals. Metals were seen like as kind of like you will always need metals, right? You cannot build everything with carbon nanotubes or with plastics or whatever, right? You need metals to build stuff that lasts, right? But metals research was seen kind of like, old school and not very exciting. Now, if you go to Nature Science, Nature Materials, every issue has an additive manufacturing paper or a metals paper, right? So high entropy alloys and additive manufacturing are the hot topics in the US, and they have revived, the field of metals research. And I think it's a very interesting area. It's very difficult. You have to understand many things if you want to do something useful in additive, but there are a lot of opportunities. And of course, I think that there's a very strong connection to industry, right? So additive manufacturing is research that can be done at the university level and the national lab level, but that has dramatic, impact on industry, right? And what our country needs, what Mexico needs, is more advanced industry to increase the value added of the products that we sell internally and that we sell to other countries, right? So I think that additive manufacturing is an excellent area to be in if you start now, because it didn't become important until 10 years ago, if you think about it. It was there, but not many people were doing it. The Journal of Additive Manufacturing is 7 years old, if I'm not mistaken, right? So, or maybe, I may be wrong in that, but it's not like a super old field. And a lot of the people who are doing additive manufacturing now, we didn't start doing additive manufacturing. I got into additive manufacturing 5 years ago or 6 years ago. Okay. So if you start doing additive manufacturing now, you're going to become an expert in additive manufacturing when you graduate and when you start working for industry or academia or national lab and so on. As an advertisement, if you're interested in our groups, mine and the group of Malak and Elwani and Karaman, and you want to do a PhD or you want to do a postdoc, we may be looking for people. We're starting a lot of new projects. I'm starting like 3 or 4 projects in January, on additive manufacturing of refractory alloys, like ultra high temperature alloys. So there are a lot of opportunities at Texas A&M. It is a great school. And, we have one former student of Juan and others in my group now. So if you want to come and get a PhD or do a postdoc at Texas A&M and you're doing interesting work, please send me an email. I'm gonna type my email in the chat in case you're interested in contacting me. So with that, I would like to thank you. I'm going to switch to Spanish. Muchas gracias a todos por su atención. Espero que les haya gustado la plática.
Muchas gracias.
Y ha estado muy bien la conferencia. Hey, Juan.
Gracias, Raimundo.
Juan quiere saludarte.
Muchas gracias por todo.
Claro, gracias.
Muchas gracias por el ofrecimiento. De igual forma, creo que el CONMAD y CIDESI te hacemos el ofrecimiento a ti y a tu grupo de colaborar y de trabajar juntos. Y tenemos las facilidades para hacer bastantes cosas en cuestiones de manufactura aditiva. Esperemos que esto sea un par de aguas para seguir adelante, ¿no?
Sí,
yo creo que en todo
una
lo que
vez,
se habló.
Una vez que se termine COVID, sí los voy a visitar allá.
Por favor, doctor, aquí lo esperamos.
Claro.
Muchas gracias.
Claro, me gusta mucho
Muchísimas
Querétaro.
gracias por su tiempo.
Hasta luego.
Gracias, hasta luego.
Hasta luego.
A toda la gente que sigue conectada, les queremos nada más informar que vamos a terminar esta sesión y a las 3 de la tarde retomamos la sesión con el doctor Diego Espinosa y volvemos a iniciar la transmisión. Muchas gracias y nos vemos en un rato. Va a ser la misma liga que ya tienen, la seguiremos compartiendo en todas las redes sociales del consorcio y del CIDESI. Gracias.